Hey everyone, and welcome back to Educator.com. This lesson is on vectors and scalars. Our objectives are going to be to differentiate between scalar and vector quantities, to use scaled diagrams to represent and manipulate vectors, being able to break up a vector into x and y components, finding the angle of a vector when we're given its components, and finally performing basic mathematical operations on vectors, such as addition and subtraction. So, when we talk about vectors, what we're really talking about are different types of measurements in physics, different quantities. And there are really two types, scalars and vectors. Scalars are physical quantities that have a magnitude or a size only. They don't need a direction. Things like temperature, mass, time. I know what you're thinking. Time has a direction, right? Forward or backward? Well, not really. When we're talking about direction, we're talking about things like north, south, east, west, up, down, left, right, over yonder, over yander. That sort of direction. Forward, backward, when we're talking about just a positive or negative value, isn't what we're talking about here. On the other hand, vectors are quantities that have a magnitude and a direction. They need a direction to describe them fully. Things like a velocity. You have a velocity of 10 meters per second in a direction. A force is applied in that direction. Or a momentum. You have a momentum in a specific direction. And vectors we typically represent by arrows, where the direction of the arrow tells you the direction of the vector, obviously, and the length of the arrow indicates the magnitude or size. The longer the arrow, the bigger the vector. So, let's take a look at a couple vector representations. Let's call this nice happy blue one A, and this red one down here B. Notice they both have the same direction, but A is much smaller than B. A has a smaller magnitude than B. B is a longer arrow, larger magnitude. Now the other thing that's nice about vectors is as long as you keep their magnitude, their size, and their direction the same, you can slide them around anywhere you want. You can move a vector as long as you don't change its direction or its magnitude. So if we wanted to, we could take vector A, instead of having it there, we could slide it somewhere over here, for example, give it the same direction and magnitude, make this one go away, and now there's A. Same value, same direction, same magnitude. We're allowed to move them like that. So let's talk about how we would add up two vectors. A vector such as A and B. The little line over that means it's a vector. If we want to try and put together A and add it to vector B to get some vector C, the sum of those two vectors. Well, graphically, here's the trick. Take any vectors you want to add, however many of them there are, and if we slide them around so they're lined up tip to tail, we can then find the resultant, the sum of the vectors. So here we have A and B, but they're not lined up tip to tail. So what I'm going to do is I'm going to redraw these. So I'm going to put A over here, and B I'm going to line up so that it is now tip to tail with A. Hopefully something roughly like that. So now we have A and B lined up so that they are tip to tail. To find the sum of the two vectors, now all we have to do is draw a line from the starting point of the first to the ending point of our last vector. That must be the sum of the vectors C. All right, does it make a difference what order you add things? Well, if you think back to math, B plus A should be the same thing. And it is. Let's prove it. Let's take, and we're going to redraw this now, but we're going to do B first. So what I'm going to do is I'm going to draw B down here. There's roughly B. And now I'm going to put A on it, but I'm going to line them up tip to tail in this direction this time. So B comes first, then A. Once again, when I go to draw the resultant, I go from the starting point of the first to the ending point of the last. Notice I have the same thing. Same magnitude, same direction, same vector, same result. All right, how about graphical vector subtraction? Here we have A again and B. Put the line over them to indicate their vectors. What do we do for A minus B? Well, the trick here is realizing that A minus B is the same as A plus the opposite of B. Well, what's the opposite of B? It's as simple as you might guess. If we have B pointing in this direction with this magnitude, all I have to do is switch its direction, and there's negative B. So if I want A plus negative B, let's just redraw them again, now tip to tail. We'll start A down here. There's A. And negative B goes something like this. So A plus negative B, which is A minus B, we go from the starting point of our first again to the ending point of our last. A plus negative B equals C. All right, basic vector manipulation. Now, when we have these vectors and they're lined up at angles, oftentimes we can simplify our lives from a math perspective if we break them up into component vectors or pieces that add up to the sum. And if we pick those pieces carefully so they line up with an axis, the math gets a whole lot easier. And I'm a huge fan of easier math. So let's assume that we have some vector A right here at some angle theta from the horizontal. We could replace this with a vector along the x-axis and a vector along the y-axis. Notice that the blue vector plus the green vector, if we add them together, gives us that A vector, the vector we started with. So we're going to take this A vector and we're going to replace it with this blue one and this green one. Two vectors that are a little simpler to deal with mathematically. Let's call this the x. Oops, let me use a color that's consistent. Let's call this the x component of A, and we'll call this the y component of A. How do we figure out what those are? Well, if you notice here, we've made a right triangle, where here's our hypotenuse. This is the opposite side because it's opposite the angle, and AX must be the adjacent side. It's beside the angle. So now I can use trig to figure out what AY is. AY, since it's the opposite side, is going to be equal to A, the hypotenuse, times the sine of that angle. On the same note, AX is going to be A times the cosine of theta, because this is the adjacent side. Remember SOHCAHTOA? Sine of theta equals the opposite side divided by the hypotenuse. Cosine of theta equals the adjacent side divided by the hypotenuse. And tangent of theta equals the opposite side divided by the adjacent. All we're doing is we're finding out what this opposite and this adjacent side happens to be. So we can break up this vector A into components AX and AY that are going to be much easier to deal with mathematically. We could also go back to finding the angle of the vector. If we know two of the three sides of these triangles, if we know both of the components, we can find the angle. If we know the hypotenuse and the opposite, we could find the angle. How do we do that, though? Well, let's go back to our trig functions. Tangent of theta equals the opposite over the adjacent side. Therefore, theta must be the inverse tangent of the opposite side divided by the adjacent side. But what if we don't know opposite or adjacent? Well, sine theta is equal to the opposite over the hypotenuse. So if we know opposite over hypotenuse, we can find theta by taking the inverse sine of the opposite side divided by the hypotenuse. Or what happens if we don't know the opposite side? We know the adjacent side and the hypotenuse. Well, the cosine of theta is equal to the opposite side over the, is equal to the adjacent side, adjacent over the hypotenuse. Therefore, theta equals the inverse cosine of the adjacent divided by the hypotenuse. So if you know any two sides of this right triangle you're making with components, you can find the angle using your basic trigonometry. Now let's talk for a few minutes about vector notation. You can express vectors in many different ways. You can just draw it on a sheet of paper. We can express it mathematically. But we want to do this as efficiently as possible. So I'm going to show you some examples in 3 dimensions, but you can always scale those back to just 2 dimensions. So let's start off by making an axis. We've got y, x, and let's have a z-axis coming out toward us. If we have some vector a, we could express it as having an x component, a y component, and a z component. On the other hand, though, we could also look at it in terms of what are known as unit vectors, where if we take a vector of length 1 along the x-axis, magnitude 1 along the x-axis, we're going to call that specific vector I hat, length 1 along the x-axis. In the y-axis, we'll do the same thing. A vector of unit length, of length 1 in the y direction, we'll call j hat. And in the z direction, same idea. A vector of length 1 in the z direction, we'll call k hat. Specific vector constants. So we could write a now as some value, it's x value times I hat, plus its y value times j hat, plus its z value times k hat. So whatever the x value is, you multiply it by a vector with unit length 1 in the x direction. Y value times a unit vector of length 1 in the y direction. And the z value times a unit vector of length 1 in the z direction. Another way to express vectors. That can be very useful when we get to the point of doing vector addition. Let's assume that we have our axis here again. Y, x, and z. And here let's put a vector that is, let's go 4 units in the x, 1, 2, 3, 4, 3 in the y, and out toward us 1. So let's call this point P 4, 3, 1, which is defined by some vector P, which is 4 units in the x, 3 in the y, and 1 in the z. And let's also define another vector Q. Let's go 2 units in the x. We won't go any in the y, 0 in the y, and let's come out toward us in the z direction, 1, 2, 3, 4. Let's call that point Q, which is 2, 0, 4. And we'll label that vector from the origin to that point as vector Q. How do we add these vectors in multiple dimensions? Well, what we could say is that vector R is going to be equal to vector P plus vector Q. Therefore, let's write P as equal to 4, 3, 1 in this bracket notation for vectors, and vector Q is equal to 2, 0, 4 in vector bracket notation. Well, if the left-hand side is equal to the right here, and the left-hand side is equal to the right here, if we add the left-hand sides and add the right-hand sides, they should still be equal. So what we can say then is if we add those two, we can add those two. Therefore, P plus Q which is equal to our R must be equal to, well, in vector bracket notation, we add up the x components. 4 plus 2 is 6. We add up the y components. 3 plus 0 is 3. And we add up the z components. 1 plus 4 is 5. So the resultant, R, would be 1, 2, 3, 4, 5, 6 units in the x, 1, 2, 3 in the y, and then 5 toward us. Something like that in 3 dimensions. Adding up vectors using that vector notation can make things a lot simpler, especially when you don't want to go drawing all the time. Let's take a look at a vector component problem. A soccer player kicks a ball with an initial velocity of 10 meters per second at an angle of 30 degrees above the horizontal. Find the magnitude of the horizontal component and vertical component of the ball's velocity. Well, I'm going to start off with a diagram here. A y-axis and an x-axis. and realize that the soccer player is kicking the ball with an initial velocity 10 meters per second. So there's our vector, 10 meters per second at an angle of 30 degrees above the horizontal. We want to know the horizontal component and the vertical component. Well, as you recall, if we want the vertical component, if this is our initial velocity v, then the y component of that velocity is going to be v, 10 meters per second, times the sine of 30 degrees. 10 meters per second sine 30 should be 5 meters per second. And in similar fashion, the x component of velocity v is going to be v cosine theta again, or 10 meters per second, times the cosine of 30 degrees. Cosine 30 is 0.866, so 10 times that is going to be 8.66 meters per second. We've broken up v into its x and y components. All right, another one. An airplane flies with a velocity of 750 kilometers per hour, 30 degrees south of east. What is the magnitude of the plane's eastward velocity? Well, let's draw a picture again. North, south, east, and west. And the airplane flies with a velocity of 750 kilometers per hour, 30 degrees south of east. That means start at east and go 30 degrees south. So I'm going to draw its velocity as roughly that. 750 kilometers per hour at an angle of 30 degrees south of east. If we want its eastward velocity, the eastward component, that means we want its x component here. X component of its velocity, Vx, is going to be v cosine theta, or 750 kilometers per hour, times the cosine of 30 degrees, 0.866, should give us something right around 650 kilometers per hour. Let's take a look at another one where we have to deal with vector magnitudes. A dog walks a lady 8 meters due north and then 6 meters due east. I'm sure you've all seen that before. Big dog, little person trying to walk it, and really the dog's in charge. Determine the magnitude of the dog's total displacement. Well, if the dog walks the lady 8 meters due north, we'll have a vector 8 meters north, and then 6 meters east. Determine the magnitude of the dog's total displacement. All right, well, if we started down here, I've lined these up tip to tail, so the total displacement, which is the straight line from where you start to where you finish, is going to go from here right to there. That's the displacement. How do we find the magnitude of that? Well, if you look, that's a right triangle. We can use the Pythagorean theorem. A squared plus b squared equals c squared, where a is our 8 meters, b is our 6 meters, c is going to be our hypotenuse, or the displacement. Therefore, this is going to have a magnitude of the square root of 8 meters squared plus 6 squared, or square root of 64 plus 36, square root of 100, is going to be 10 meters. And say we wanted to know what this angle is. If we wanted to know that, we could take a look and say, the x component of that green vector is going to be 6 meters. The y component must be 8 meters. Therefore, if we wanted that angle, theta is going to be the inverse tangent of the opposite side over the adjacent, which is the inverse tangent of 8 meters over 6 meters, which comes out to be about 53.1 degrees. That would be our angle theta there too, if it had asked us for the angle. It only asked us for the magnitude of the dog's total displacement, which we found to be 10 meters. All right, let's take a look at some more vector addition. A frog hops 4 meters at an angle of 30 degrees north of east. He then hops 6 meters at an angle of 60 degrees north of west. What is the frog's total displacement from his starting position? All right, this just screams for us to draw a picture here first. So let's draw our axes here. I'll have a y-axis and an x. And as we look at this, there's our x, here's our y. The frog starts out 4 meters at an angle of 30 degrees. All right, there's 4 meters at an angle of 30 degrees. Then he's going to go and hop 6 meters at an angle of 60 degrees north of west. So 6 meters at an angle of 60 degrees north of west is probably something kind of like that, where that angle is 60 degrees north from west. And that's 6 meters long. That's 4 meters long. What is the frog's total displacement from his starting position? Well, I could find that out graphically by drawing a line from the starting point of the first to the ending point of the last. Or if I wanted to do this analytically a little bit more exactly, I could take a look. If our blue vector is A is equal to, well, its x component is going to be 4 meters cosine 30 degrees. And its y component is going to be 4 meters sine 30 degrees. Our b vector, there in red, is going to be, well, we've got 6 meters cosine 60 degrees for its x component, but it's to the left, so let's make sure that's negative. And its y component is 6 meters sine 60 degrees. So if I wanted to find the resultant, the sum, vector c, c is just going to be equal to a plus b. So that's going to be 4 meters cosine 30 degrees, the x component of a, plus the x component of b, negative 6 meters cosine 60 degrees. So that'll give us the x component of c. And for the y component, we add their y components together. 4 meters sine 30 degrees from a, plus 6 meters sine 60 degrees from b. And when I do the math here, I find out that c equals, well, 4 cosine 30 plus negative 6 cosine 60. That's going to be about 0.46 meters. And the y component, 4 meters sine 30 degrees plus 6 meters sine 60 degrees, comes out to be about 7.2 meters. So there is our c vector. 0.46, so not much in the x, 7.2 in the y. While we're here, let's find out its magnitude and angle. The magnitude of c, I take the c vector and I take its absolute value, I can find out by using the Pythagorean theorem again, since I know its components. That's going to be the square root of 0.46 squared plus 7.2 squared, which comes out to be about 7.21 meters. And if we wanted its angle as well, I'm expecting a big angle here, just by taking a look at the picture. Theta is going to be equal to the inverse tangent of the opposite side over the adjacent side. The opposite side is the y, 7.2, over the adjacent 0.46, for an angle of 86.3 degrees, which is, over here, 86.3 degrees north of east. So we could express the vector with a magnitude and a direction, or we could express it just by leaving it in this vector bracket notation. And if we wanted to, we could even have written it as 0.46 meters I hat plus 7.2 meters j hat. They're all equivalent. All right, let's take a look at one more sample problem, the angle of a vector. Find the angle theta depicted by the blue vector below given the x and y components. Well, since I'm given the opposite side, opposite the angle theta, and the adjacent side, the side that's beside the angle but not the hypotenuse, I'm going to use the tangent function, since tangent of theta equals opposite over adjacent. Therefore, theta is going to be the inverse tangent of the opposite side over the adjacent side. Or theta equals the inverse tangent of the opposite side 10 divided by the adjacent 5.77, or 60 degrees. Hopefully this gets you a good start on vectors and scalars. We'll be using them throughout the entire course. Very, very important. Thanks for watching Educator.com. Make it a great day.